Hi, this is Victoria Forsyth from Astra. In this presentation, I will describe the effort to improve the ionospheric data assimilation, DaytoDay, and especially its covariance matrix formation. This presentation would focus on the horizontal component of the covariance matrix, and another presentation here at CEDAR is about vertical correlation. So please check it out if you're interested. So we're using DaytoDay ionospheric data assimilation. It combines background empirical model we use in IRI 2016 and data. It uses 3D VAR approach to find the solution. The data sources that we're using are the GNSS slant total electron content, plus radio occultation data, plus point measurements from ionozones, coherent scatter radars, top sounders, in situ density measurements, and other related to density data such as radiance. So important component of DaytoDay is the background model covariance matrix. It determines the correlation between model errors and how the transition happens from data-driven regions to model-driven regions. This matrix is very large and it's close to impossible to find its true representation. Well, first of all, because we don't know the true ionosphere everywhere on the globe, plus it's computationally very expensive. It's a very large matrix which has n by n size, where n is the number of grid points in data assimilation. So we need to find the ways to model this matrix. There are three assumptions that have been used. That this special correlations are separable horizontally and vertically, that the vertical part can be modeled as the Gaussian, and that horizontal distribution can be modeled as an elliptical Gaussian. Here is the equation that describes each component of this matrix. So the correlations are determined between points I and J. So this matrix can be separated into three different ones. The first one would explain the variance of the model. The second one would be in charge for the vertical correlation distribution. And the third one, this presentation is about this component, is about the horizontal correlations. So they're modeled as the elliptical Gaussian. This portion shows the elliptical shape. And the distances are in terms of great circle distance from point I to point J. And then the elliptical shape would be dictated by the azimuthal angle alpha, and how wide the ellipse is in zonal direction would be determined by L sub phi, and in meridional direction would be determined by L sub theta. So the goal of this presentation is to find the global distribution of these two parameters of zonal and meridional correlation distances. So we used the 20 years of Jet Propulsion Laboratory global ionospheric maps with 2-hour resolution, and we used the IRI 2016 model to find model errors. So model errors were determined as vertical total electron content of IRI minus vertical TSC of global ionospheric maps. This would be the difference between the two, referred to as model errors. Then we converted them into geomagnetic coordinates, and we binned them in season, winter, summer, equinox, in solar flux, low, moderate, high, and in 12 universal time frames. So the combination of model errors for one bin would represent the ensemble, and we would find correlations for different points on the globe among these ensemble members. For example, if the reference point is shown here with a black dot, then the correlations around this point would be shown with the color. Correlations are high, close to the point, they're equal to 1, and then they drop from 1 further away from the point. His panel B shows the same information, but as a function of azimuth, and y is the great circle distance from the reference point. So right away we can see that the distribution is not isotropic in azimuth. For example, at negative 90 degrees of azimuth, the correlation drops faster than at positive 90 degrees of azimuth. So the correlation lengths were calculated in 36 azimuthal directions with 10 degrees apart. And they were calculated as the location where the correlation drops to 0.8. So all of these white dots show the correlation distances from the reference point. Then the zonal correlation distance was found as average of correlation distances at negative 90 and at positive 90, and the meridional correlation length was found as average between correlation length at 0 and at 180. So again, the zonal correlation length would determine the extent of the correlations in east-west direction, and the meridional correlation in north and south direction. Here is how the global distributions of zonal correlation length and meridional correlation length looks like. So the correlation length ranges from about 10 to 50 degrees of great circle distance. And it has some peaks. For example, zonal correlation length is higher close to equator, somewhere inside of the equatorialization anomaly. And also it has two peaks around sunset section at mid-latitudes. And meridional correlation length doesn't have the peak inside of the equatorialization anomaly. It has a peak prior around sunrise sector. Here's how they change with different solar flux conditions. Here is the panel that I showed before for high solar flux. For medium solar flux, the peaks are reduced. And for low solar flux, interestingly, everything shifts to the northern hemisphere. So the peaks are now at the northern hemisphere and not symmetric. So there is some interhemispheric asymmetry that's been introduced in the lower solar flux condition. To analyze the magnetic local time dependence, so here zonal and meridional correlation lengths as a function of MLT, and different color represents different magnetic latitude. So you see that zonal correlation length doesn't have a well-pronounced MLT dependence, where the meridional correlation length does. It has two peaks. One is around sunrise, another is around sunset. That's how the two other seasons look like. Here is summer and here is equinox. So you see that during the equinox, the peaks are higher for the meridional correlation length. And both summer and equinox also doesn't have a well-pronounced MLT dependence for the zonal correlation distance. Previous studies have shown that the day-to-day atmospheric variability can be used as a proxy for correlation length determination for the atmospheric data assimilation. We have used the same data set to find the day-to-day variability, which was found as difference between the two consecutive days. So basically vertical TAC at one time frame minus vertical TAC at the same time frame of the previous day. And this is how the results look like from the previous slide for the IRI-derived correlation length. And this next column is derived for the same bin for the day-to-day atmospheric variability. You see the correlation lengths derived from this method are about twice smaller than correlation lengths derived from IRI model errors. Plus the distributions look really different for high latitudes. They are pretty flat, no variation with MLT, those dark blue and dark red colors, where it's not the case for the IRI-derived correlation length. The only similarity that we could spot is that meridional correlation lengths from day-to-day variability also had two Hopf distribution. One peak is around sunrise, another is around sunset. But the one at sunrise was usually much higher than the one around sunset. So we can conclude that the day-to-day variability derived correlation lengths cannot be directly used for data assimilation because they look so much different than the ones derived from IRI 2016 model. In order to further investigate the anisotropy of the distributions, we did the following analysis. So for the zonal correlation length, we would find the factor that would determine by how much or one side of the ellipse is larger than another side of the ellipse. And this is explained here and showed here in panel A. So if the color is green, then it means that both L51, L52 are equal size. But you see how large those areas are with blue and red, which represents the regions with high anisotropy. Same was done for the meridional correlation length. Again, when the fraction is equal to 0.5, this green color, it would mean that the extent of the ellipse is the same in 0 and 180 azimuths. And when the color is red and blue, it means that the anisotropy is high. So this points out the important part that we need to take into account the fact that these distributions are not isotropic when we model error covariance distribution for ionospheric data assimilation. So we suggest to use asymmetric shape instead of the ellipse. The asymmetric shape would be defined the following way. We would find the correlation distances at four orthogonal directions at 0, at 90, 180, and negative 90 degrees, and call them L1, L2, L3, and 4. And then we would use the same elliptical equation, but with some condition. For example, when azimuth goes from 0 to 180, we would use L2. When it goes from 0 to negative 180, we would use L4, and so on. Same when it goes from positive 90 to negative 90, we would use L1 to describe the ellipse. And if it goes from negative 90 to positive 90, we would use L3. So this black line now shows how this the fit looks like using this asymmetric shape. So it explains the azimuthal distribution of points way better than the regular symmetric elliptical fit. And then we would use the same Gaussian equation in order to model the error covariance for ida4D. So in the conclusion, the global distributions of horizontal correlation length were derived based on IRI 2016 model errors. Significant variations was seen with magnetic local time, season, and F10.7 solar flux index. We found that IRI-derived correlations of model errors are not controlled by day-to-day ionospheric variability because the distribution of variability-derived correlation lengths looked really different from the one derived from IRI. So when we conclude that day-to-day ionospheric variability derived length cannot be directly used as a proxy for construction of error covariance matrix for data assimilation. So the results of this work can be directly applied to ionospheric data assimilation. Here is the link to the data files, not the data files, but the metadata as a result of this study. You can download them. There are netcdf files for different season, solar flux, and UT frames, and they represent the maps of zonal and meridional correlation length. Thank you very much for your attention. If you have any questions, please write me an email. Thank you.